Hey folks, welcome and good afternoon. My name is Edward Fidler. I'm the head of transport research. I'm on the smart cities team at ARC. I want to welcome you to our session on electric vehicles. Just a few housekeeping items to start. Today's session is 90 minutes. We'll have a very brief intro for myself. Then we'll have two speaker presentations. And then we'll open up to a panel discussion and audience Q&A for the second half. We ask that you please submit your questions via the Q&A function. Please don't use the chat as we won't be checking that. After this session, we have another one on transport focused on connected vehicles at 4:30 p.m. And we ask that in between the two, you visit the networking area on vFairs to chat with other attendees and analysts. So there's a lot of talk and a lot of momentum nowadays around EVs. Private drivers, commercial fleets alike are finding EVs compelling, and the space is growing rapidly. Of course, we have Tesla, Nissan, GM that have been active here for many years. Excuse me. But we also now have huge names like Volkswagen, Audi, Ford, Porsche, and many Chinese OEMs, all putting their force behind the light duty space. We also have companies like Shangji and Rivian making waves with massive orders of medium duty vans or pickup trucks. We have Volvo, Mack, Daimler, Proterra, BYD building heavy duty vehicles, trucks, buses, etc. So in 2019, there were about 7 million EVs in private hands. By the end of 2020, about 10 million. And of course, this is excluding delivery vans or the hundreds of thousands of fully electric buses that you mostly find in Chinese cities, and the millions of electric 2 and 3-wheelers that are mostly found in Asia. So the space is growing incredibly rapidly. It's just astronomical. So why the switch? Well, here are some features of EVs. They consume less energy per mile than fossil fuel vehicles. They have fewer moving parts, roughly half. Zero tailpipe emissions. They're nearly silent. They provide instant torque. And even a partially depleted lithium-ion battery is going to have a high resale value. So let's look at energy costs. EVs convert energy to propulsion far more effectively than fossil fuel vehicles. Today's battery electric vehicles have an MPG equivalent around 3x that of a comparable fossil fuel vehicle. So here you have a graphic showing dollar cost per mile of a battery electric in orange versus an equivalent fossil fuel vehicle in blue for urban markets in 3 major regions. So even though this number will vary by, local electricity prices, fuel tax, and things like that, you see that EVs have a far lower per mile energy cost. In fact, it's at most half, sometimes a third. So it's quite dramatic. EV owners and fleet operators don't have to worry about oil changes, spark plugs, wiring, ignition coils, engine sludge, all kinds of factors. That's especially attractive for fleets, right? And that's why we're seeing all kinds of fleets starting to electrify, from ride hail, car share, delivery, e-commerce, city buses, trucking logistics, urban construction, underground mining, and even law enforcement. And so a lot of that comes down to this, right? Total cost of ownership. So this graphic here shows the net present cost of ownership as it develops over the life of a vehicle. So as you can see, starting on the left-hand side, the electric vehicle has a higher upfront cost, right? The orange line starts higher. But as those operating cost advantages in lower energy and maintenance costs that we discussed accrue, the total cost of ownership ends up being lower for the battery electric during its life. And this graphic doesn't even consider the sizable resale or salvage value for the lithium-ion battery. Now, lower costs are one thing, but if you rely on petroleum, then your fleet has to deal with hugely volatile prices for one of your largest input costs. So here's just a simple graphic. It's an index on top showing commercial power versus diesel prices over a 10-year period. So as you can see, the diesel prices spike 60% in 2 years, and they drop back even lower, and they spike again. In the meantime, the commercial power prices are flat. And the graph below shows the actual standard deviation, so a measure of the variance of those prices over this period. So the variance of the diesel is 10x. Now, there are plenty of non-financial benefits for fleets too. Less air pollution, so that's your particulates, your NOx and SOx. Lower greenhouse gas emissions. It reduces their exposure to a growing body of regulation in regards to pollution. EVs tend to provide a better experience for customers as well as their operators. And it does wonders for a fleet and a company's image and PR. And so for all these reasons, fleets are leading the way. We have delivery companies, your FedEx, UPS, DHL. They're rolling out e-delivery vehicles. Amazon ordered 100,000 electric vans last year, or 2 years ago at this point. You have local taxi companies. You have cities and airports using electric buses. Waymo is ordering tens of thousands of self-driving EVs. And Lyft and Uber are incentivizing their drivers to electrify as well. Now, of course, there are some challenges here. Unfortunately, a major set of challenges is under misconceptions and a lack of public knowledge. So some issues like range anxiety or a perception of living with an EV as being inconvenient, or that say there isn't much charging infrastructure out there. So all of these fears and these ideas, they were true, they were valid maybe 4 or 5 years ago, but they're really not nowadays. So the average EV that you might buy today has a 200 plus mile range. It's more convenient than a fossil fuel vehicle because the vast majority of your charging is done at home or at work. So you park the vehicle, plug it in, you come back, you have a full battery. There are many, many models available now, and plenty are being released of different sizes, different power capacities, etc. And for those times when you do have to charge on the road, the nation is just covered in fast charging infrastructure now. So on the bottom here, we have 2 charging maps, one from ChargePoint, one from Tesla. And these are mostly fast chargers. And as you can see, all the US population centers and major highways are covered. Another angle here is, how does the grid handle so many EVs, right? Tens of millions, fleet vehicles, etc. So the graphic on the top right is something called the shark curve. So it's showing um, net load from charging from EVs. And as you can see, canonically, many people plug in when they come home from work at 5 or 6 p.m. And that's just when the sun goes down. So that's when solar generation drops. So how do you deal with that, right? So to answer some of these questions and to walk us through a real life e-fleet deployment, we're going to have Gary Miskell, the CIO of Santa Clara Valley Transport Authority, talk about his organization's e-bus deployment. And then we're going to have Rick Riss. He's the lead energy analyst at ARC. Give us the grid and energy perspective for all this. And then joining us on the panel will be Paul Lipkin. He's the Senior Director of Energy Solutions at ChargePoint. And that's the company that helped make Gary's deployment a reality. So with that, we'll welcome Gary Miskell.
Edward, you have to quit sharing, I think. Thank you. Okay, let's see.
Yeah, swap those monitor views up there under display.
Yeah, I'm working on that right now.
Okay.
Interesting, it didn't stick.
Yeah.
Okay. Well, thank you. So VTA basically a few years back has started, and procured 5 electric vehicles. We also went off and acquired some funding from the California Energy Commission. Now, VTA is what we could think of as a medium-sized transit agency. We currently, pre-pandemic, we were doing about 32 million passenger trips a year. We have 470 buses, around 98 train cars, and around 230 paratransit vehicles. Now, VTA is a little unique. VTA is also a congestion management agency. So we also get into doing construction and a lot of working with the different 15 cities in our jurisdictional area on during, highway projects and bikes and other kinds of modes of transportation. So in June of 2017, we got funded for this project. And for this project was about a $3 million project. We actually had 14 partners that all worked together on this project. So you can see it wasn't small. We had, and we'll kind of talk about a number of the different players such as, ChargePoint, NREL, Clever Devices, and Prospect Silicon Valley. Actually, Prospect Silicon Valley took the lead on the project and actually did the initial grant, got the grant from the CEC. So kind of what is the project that we're trying to talk about? So we broke this project up into 2 phases, which we call the vehicle to grid integration project. So the first phase was to go off and develop all the requirements and all the different systems that we would have to touch and integrate, because the whole idea here was to try to make electric buses and our regular fleet almost identical in the terms of manpower to support the project, the vehicles while they're in the field or while they're in the yard. So we basically defined all the requirements, and then we started off either in building the EMP, which is Energy Management Platform by ChargePoint, as well as the different applications that we wanted to get changed, such as from Clever Devices or Trapeze or SAP, to go look at what changes those applications needed to do to be able to include and handle all the new parameters. Then the second phase of the project, which started, more like around January, February of this last year, where we actually then started building all the integration between the applications so that all the different applications, we were trying not to have manual data moving from application to application. We wanted all the applications, we wanted the bus to talk to ChargePoint, we wanted or to Clever Devices, and all these systems to be all integrated and talking to each other. So let's talk a little bit about so from ChargePoint, we basically had installed 6, CPE 250 chargers, which that was done in June of 2018. And as you can see on the right-hand side there in the graph, you can see for all of basically 2019, our energy usage was kind of low as we were still learning how to test and learning how to use the different systems. And then somewhere around the March, April timeframe, as you can see, our energy usage really goes up considerably, where we now have the vehicles out on the road and actually in production and in use. So now we're really talking about revenue service. And you can see COVID kind of takes a little dip in there. So you can see where for a while we were actually not using the buses during COVID, and now we're actually have those vehicles back on routes again, and we're off using them at full production. And we've also taken delivery of an additional 5, so we now have 10 vehicles in service. So let's look a little bit at the power that we're consuming. Now, interesting on this graph, just real quick, the graph starts at noon, and so the middle of the graph is at midnight. So you can see back in June of 2020, basically the orange is actually when we are consuming power into the chargers. And you can see this site has 960 kilowatts of solar. So you can see during the middle of the day, like around noon, 1, 2, 3, and 4 o'clock, we're dumping a lot of power back on the grid. And the lower graph, which is in the December timeframe, when we're actually there's less energy generation because of more cloud cover, rain, and the whole, where the earth is. So there's a lot, but we're still generating surplus power back onto the grid. And as you can also see, we're actually doing a lot more charging of vehicles. Now, interesting about that is the charge management system is really keeping that to where we're, even though we may plug buses in earlier in the day, like when a bus may come back at 5 or 6 o'clock, it's actually not charging the vehicle. So the energy management platform is level loading the load and trying to keep that level throughout the evening hours so that the buses are then ready for pullout at 4:30 and 5 and 6 o'clock the next morning. Now, another one of our partners, which was Trapeze. Trapeze basically is the application that you assign the bus and the driver to a block. So a block, of course, is the work that bus is going to do, that next day. So in the evening, as the buses come back, they would get assigned. Trapeze would then assign them to the next day's work. And it also takes into account any maintenance issues. And it says, well, if a bus isn't going to be available for work, then it would assign a different bus to that particular task for the next day. And then that information is then transferred to the ChargePoint energy management platform, so that way now the bus knows what work it has to do and how much energy is going to be needed to be put back into the vehicle to do the next day's operation. So the real value here, as you would expect, is that one is operations is not guessing at what vehicles are available and what vehicles are then assigned to which route and what driver is going to assign to be assigned to which vehicle that following day. Where prior to all this, system going into place, they had to try, and of course, if the buses are a small number, it's not a big issue. But as the bus quantity starts going up, that becomes a bigger and bigger issue, is to make sure that what bus is going to be assigned to the next route that day, and taking into account all the different things like temperature, and is it going to require extra heat or extra cooling? And so we have to derate the vehicle as far as its distance goes, depending on what the environmental conditions are. Now, Clever Devices is what we call our CAD AVL, which is are, so it's monitoring the vehicle basically while it's in the field, and so in it also takes into account whatever weather, the environmental situation, hills, whatever, and what traffic and congestion. So it's constantly evaluating the bus in the field to make sure that the bus basically, so if it felt that, if we assigned it to like a 180-mile block, and all of a sudden the temperature becomes 10 or 15 degrees higher that day, then Clever Devices is monitoring the bus and monitoring the energy consumption. And it might say that, well, because of the higher, cooling load, the bus isn't going to be able to make the entire block by the end of the day. So the dispatcher now has an alarm that would then trip, and now knows that they need to pull that bus off and swap it out with a different bus. So far, we've never had that problem, but just in case, the system is sitting there constantly monitoring and tracking that. And if you say, well, gee, that can't be all that hard. So here's an example of just on the Clever Devices, so we're actually pulling data off of the bus and, off of the vehicle on its energy consumption, how much energy it's recuperating. It provides all that information into the report system. So I'm not going to go through all the data flow in detail here, because that in itself would take 30 minutes, but just gives you a feel for of how complex and how well thought out we made the whole system. So kind of as a summary on the Clever Devices side, basically it's monitoring the schedule, it helps in the assignment with Trapeze. It provides information for the charge management platform so that it's helping on recommending what it needs to do for the next day. It's monitoring it during the day, so it both provides the driver and the dispatcher real-time data on how well the vehicle is performing and any kind of alarms that might trip, as well as it now provides us a great deal of planning data that we can look at historically as to what the parameters, the temperature, are the conditions of that day, the loading on the vehicle, how many passengers there were, what implications, or the driver, so this also provides us a lot of detailed data about the driver. Now, another one of our partners was NREL, which is the national, laboratory there out of Denver. So they basically, focus on, energy efficiency, renewable energies, and things like that. And so they provided logging devices that we put on 30 of our hybrid buses that were spread out over all 3 garages. And of course, we also installed them on the Proterra buses when we got those. And the whole idea was to go create a very nice, real world data as to how well did this, diesel hybrid bus operate on this route, so that we could then compare it accurately to the electric bus. So now we're actually taking actual data and comparing it to actual data. So that means we got a very accurate picture on what the diesel miles per gallon was versus the equivalent in electrical energy, miles per gallon were. And we looked at the duty cycle, we were able to look at distances, and we look at actually how efficient the drivetrain was within the vehicle. And we were able to get how many kilowatts per mile the electric vehicles actually did. Now, one of the other things, and actually NREL did about 7 or 8 different analysis, but for time, I thought I'd just talk about a couple of them. And then another thing that they did is actually they measured with great accuracy exactly what was the impact of CO2 or SOx or NOx. So what were these actual measurements from the different vehicles? And then how did they compare to each other? And we took into account the actual, energy, how clean the grid was. And we added that into it. So it was really an apples to apples comparison. Luckily, the California grid, especially where we are, is actually a pretty clean grid, but we took that into account. So then kind of let's see how well did the energy management platform actually work. So this is, so we kind of measured it with the energy platform off and gave you some actual days. And you can see how the charging platform or how the chargers basically, peaked up. And, so we hit quite a few peaks on a day-to-day basis and hour-to-hour basis, where with the energy management platform turned on, as you can see, it really does clip those peaks way down and still made the vehicles ready to go and service the next day. So as we all know, the operator driving an electric vehicle makes a big difference in terms of how far that vehicle will go or what your state of charge, which is the SOC, is at the end of the day. So all of our electric buses are 440 kilowatt hours, and we basically derate them down to 356 kilowatt hours. So we never take a bus below 356 kilowatts in consumption. And so what that does then is that gives us, kind of a cushion so that we're never depleting the battery pack. And it guarantees that we can always get the bus back home if necessary. So when we first started running the buses, if you notice the slope of the curve, which is critical, and that basically tells you what your kilowatts per mile are. So in the beginning, we were running the buses on 160-mile routes or blocks. So the buses and the dots basically show where the vehicle was by the time you got the bus back to the yard, what the state of charge was at the end of the route or the block. And then on the right-hand side, which was later, as we continued to work with the drivers and the system, and if you notice, the curve is now flatter. So now we were getting something like 1.7 kilowatts per mile. And we were now running the buses on 177-mile routes and blocks. So you can see both we were actually returning the vehicles back to the yard with actually more power left in them. So what are some of the key lessons learned? The EMP, can support the increase in the EV charging scale. So one of the things that we did was we tested and validated. As an example, we had one charger, and we had really 5 chargers that are in normal operation, and we have 10 vehicles. So we validated that indeed we can run, twice as many vehicles per charger, charge the vehicles up, swap them out, and then finish charging the rest of the fleet. And the energy management platform manages that process, as well as the energy management platform is actually managing, where, how to get the least amount of power or the cheapest power, to the vehicle. Now, the other thing we looked at, which we haven't actually done yet, we looked at our routes and how could we get routes that we break the routes up where we run a morning route, bring the vehicles back in, charge them in the middle of the day for a few hours, and then put them back in service, and with a minimum of extra cost for deadhead time and things like that. And that way we could use that solar energy generation, because remember, we have excess energy at the middle of the day, and how we could actually consume that energy into the buses. As well as, the rates are changing. So today we're on an A6 rate. We're about ready to roll off of that rate. And in California, we have a new set of rates coming in that actually peak is no longer in the middle of the day. It's actually from 4 to 10 p.m. or 9 p.m. And that's when the most expensive power in our area will become. So some other lessons learned is we learned that basically the operator training and working with the operators is really critical to the vehicle performance, and that the yard management platform really made management in the yard, so much easier. We definitely, with the energy management platform, could prove a 15 to 25% reduction in savings and power usage. And we also tested bidirectional, or we actually did an assessment on bidirectional vehicle to grid, where we could actually, we're taking energy from the vehicle and sending it back to the grid. Basically we were probably a little bit too early to do a lot of it, to actually be able to validate this. And that because the vehicles, the early Proterra vehicles didn't support bidirectional power. And so, but today the latest vehicles and the latest chargers can be made to do bidirectional power. But also the use case for transit agencies doing bidirectional power is pretty weak and pretty low, because our fleet is actually in the field during the middle of the day. And then at the end of the day, when the buses are all coming back, they're pretty much depleted. And so there really is not a use for PG, because we haven't charged the vehicles up. So there really is no energy in the vehicles to be put back onto the grid. So the only time we really have a fleet of vehicles in the yard with power is really about, from 2 to maybe 5 in the morning, which is typically not your normal power outage, or when PG&E or the utilities typically needs energy and power. We did show that like school buses, where they have a morning route, they come back in the middle of the day, they can be charged with solar, and then they do a really short afternoon run, and then they're back in. So most of the vehicles are back in the yard, and can typically be charged by 5 or 6 in the afternoon. Now, if there's a power outage in the afternoon, when everybody comes home from work and our air conditioners get kicked up, there actually would be power, as an example. So what would this, so what did we learn from all of the whole infrastructure? So when originally we were assumed that there would be one charger for every vehicle. Then we proved that we could have one charger for every 2 vehicles. But if we now look at where is the whole charging industry going, is an example for fleets. So now, charging companies like, ChargePoint and Proterra are both now making much larger chargers. So here's an example, is a 1.5 megawatt charger, and it has 20 dispensers. So literally you can plug 20 buses into one charger. And to charge and to manage a fleet of 34 vehicles, we would basically want to purchase 2 chargers with basically 34 dispensers. The dispensers, as an example, on the right-hand side, would be held up in the air. So the actual cables would come down from the ceiling to then plug into the vehicle. And we'd use that same structure as the solar structure. And our intent would be then to add another 1.5 megawatts of solar to the whole system. Mind, we already have 960 kilowatts, or almost 0.9 megawatts of solar. And then a microgrid now to really control the whole system, along with 4 megawatts of fixed storage battery. So the idea would be is that during the middle of the day, we would actually, instead of putting that power back on the grid, we would actually store that energy into the battery system, or a good chunk of that energy would be stored in the battery system. And then when the buses come back in the afternoon, late afternoon, starting in around that 7-8 o'clock time frame, that will end up being the most expensive power. But if I've stored my solar energy in the battery packs, I would then be able to start charging the vehicles at that 7, 8, 9 o'clock time frame, and not use power from PG&E, but consume that power out of the battery pack. And then at 10 o'clock, when the power drops way back down, then we would then start using power back off of the grid. So those are some of the things that we've learned about both the charging and the charging infrastructure. And with that, Edward, I'll turn it back over to you.
Thank you, Gary. Rick?
I think I'm up next. Great.
Yes, sir.
So just a couple of comments on Gary's presentation. Very excellent, very interesting. Certainly when you see the prices like they had in Texas on the electric grid, where they went up by a factor of 1,000 almost. I mean, the prices went out of sight. Boy, they really could have used vehicle to grid and getting all that power from your batteries to keep a few houses warm.
Yeah.
Maybe you just put an AC adapter on the back of the bus and go from house to house just to boost them up to get their heat back on. All right. But there's all kinds of interesting possibilities. A great presentation. So
Thanks. Thanks, Rick.
all right, you should be able to see my presentation now. So let me just give you a little introduction. I am an analyst at ARC. I work in the Smart Cities group along with Edward. I cover market segments for ARC, for example, in the transmission and distribution SCADA systems, microgrids, grid scale batteries, also substation automation. I actually have quite a background historically in control systems for oil and gas processes. I've also worked on the control and safety systems for 8 nuclear power plants that went to China a few years ago. I'm a light commissioner in my current town of Princeton, which owns and operates 2 wind turbines. I also designed and built my own net zero house with 8 kV of solar and a ChargePoint charger for a Tesla Model 3. So I have a lot of firsthand experience, and I try to stay connected with all the fast changing things that are going on in our electric grid. And hopefully we'll be able to share some of those with you today. So I want to start out with a little story. One of the interesting things is a lot of people think that Elon Musk started Tesla. Well, that's actually not true at all. All right. The 2 guys that started Tesla are shown here. That's Martin Eberhard and Mark Tarpenning. And it was kind of interesting what they did. These guys had a little bit of money, and I think it was Martin, the guy on the left side, he wanted to get himself a nice sports car. All right. And he kind of decided he wanted to be an environmentally conscious sports car. And this was quite a long time ago. 2003 is eons ago. And he kind of decided that, well, he didn't want to get a high performance gasoline car. And so he started making some calculations. And he was also a little bit disturbed that it was right about that time that General Motors had actually killed the EV1. But he made some calculations. These guys are both very technical guys, programmers, software types. And he made the calculation, said that, of all the propulsion options for a custom sports car, electricity is actually the best. And, he double checked these calculations. He said, that is going to be the most efficient way to propel a vehicle. So he wanted to start to get, he started looking around for somebody that would basically build him a small electric sports car. And he met up with a few guys at AC Propulsion at T0. All right. Now, this company was struggling, trying to build, AC Propulsion. I don't know if it was batteries, but basically he was trying to talk them into building him a custom sports car. And this started the relationship with Lotus to find a body. And they actually launched and started building this. And then, it kind of got a little out of hand and they needed a few investors. And at some point they actually contacted Elon Musk, and Elon Musk became an investor in the company. They said, yes, this is just a better idea. And they also said that, if we're going to build a sports car, we want to show that it has to be a compelling sports car. So they wanted to make it a little bit quick. And so this was really the beginning of Tesla. Eventually, these 2 guys left Tesla. They're both still Tesla shareholders and very much encouraging Elon. And Elon brought a set of skills to Tesla that really have allowed that company to grow like very few companies were able to. So anyway, that's an interesting story. So, of course, the elephant in the room, I made a presentation yesterday on the future electric grid. And, the elephant in the room is carbon dioxide. How is it that we're going to reduce carbon dioxide? Well, you reduce carbon dioxide by putting less in the atmosphere. Well, if you're going to put less in the atmosphere, you have to figure out, well, where's all the carbon dioxide that's going into the atmosphere coming from? And if you look at this chart, the Lawrence Livermore Laboratory has made this chart every year for the last times. I can't quite find the 2020 version of that. But, the big black coal line has gotten much smaller, and I would anticipate that it's going to get quite a bit smaller. But in addition to that, you've got to get rid of petroleum and even biogas and coal if you really want to restrict carbon dioxide. And you also look at the efficiency of those. If you're really going to, when you burn fossil fuels in an engine, a considerable amount of heat is wasted. An automotive car is 25% efficient, maybe a diesel's 30, 35 at best. You know, a stationary power plant can get over 50% thermally efficient, but you still notice that most of the heat on the right-hand side here goes to as rejected heat, kind of wasted. Except if you have electrification, very little of that heat goes to waste. And so it's mostly the big combustion engines, but even a nuclear power plant is a heat engine, and a good fraction of the heat generated by the nuclear fission products is lost as waste heat, as they use a Rankine cycle steam powered turbine system similar to coal. And the whole idea in the electric grid is that we need to electrify everything, all right, and stop using fossil fuels. That means we need to electrify transportation, and we just saw with VTA, you know, certainly some good examples. And I would also say that, you know, it also needs to be easy and simple. All of the great things that VTA was doing with energy management will make range anxiety completely go away for the bus operators. You know, once they put that infrastructure and build the infrastructure into the navigation of those buses, it'll become very clear when you have to charge, how much range you have, whether you can get to your destination. And those things are built into a lot of modern EVs today. You know, in the industrial side, you know, the big CO2 generators are steel and coal. You know, those have to be electrified. There are ways to electrify these. Obviously, in commercial office buildings and residentials, you know, we need to convert. In our town, we're a rural town in Massachusetts. We have 90% of our town uses oil heat. You know, we're trying to figure out as a utility how to convert them all to mini split heat pumps, and how to keep the power cheap and reliable so that they would find that worthwhile. So anyway, this kind of shows the big picture of the problem, and it shows how far we have to go. In the key to electrification, in fact, the biggest constraint to electrification today is actually the batteries, all right? There's not really a shortage of lithium or even nickel or cobalt per se, but there is lack of incentive for all of those mining companies to dig it out of the ground and make it into lithium, because the car companies are a little bit slow to make commitments to say, I'm going to buy this many batteries 5 years from now. And they're hedging their bets. You know, you certainly see that Tesla has made a lot of investments in order to secure the supply chain for their lithium and their nickel and their cobalt. But if you look at the evolution of batteries and the technology, what you can easily see is that within 5 to 10 years, we're going to see $50 per kilowatt hour for lithium ion. And by the way, lithium ion will be the game for electric vehicles. There's really no other competing option at the moment for lithium ion. You know, the tremendous breakthroughs that we saw with the solid state batteries from QuantumScape, yeah, great breakthroughs. It may eventually become a good battery, but in the short term, QuantumScape solid state battery is not going to win this race. So you're going to see batteries that can do 10,000 cycles. That's 1 million miles. You know, all this worry about end of life of batteries, it kind of even goes away. And also the use of batteries in electric vehicles to degrade their life, if they're used for vehicle to grid and get more charging cycles, that could have gone away, you know, had it been a priority for Tesla. Tesla could have used the iron phosphate chemistry, which is better for duration, instead of some of the nickel, manganese, cobalt technologies that are better for power and weight. Also, batteries will have a 30-year shelf life. Fast charging, I mean, we already have 250 kilowatts in a car. So I noticed that VTA said, well, they're going to have 1.5 megawatts for 20 buses. Actually, that's pretty slow. Those buses need to charge faster than that. You should be able to put almost a megawatt per bus. All right. So in any event, all of these things are coming soon in one battery. This will help to make electric cars price and function very desirable. The range issues essentially will go away. You already have quite a bit of charging infrastructure around the country. Obviously, we need a little bit more, and we need more fast DC chargers. You know, the level 2 chargers are, I don't know, if you own an electric vehicle, they're kind of toys. They're not that useful. If you're going to take a long trip, you've got to have a fast DC charger in order to make it worthwhile. So battery production at scale will expand at a tremendous rate, from 20 kilowatt hours per year to 2,000 by 2030 to 30,000 gigawatt hours per year, you know, by 2050. This is what's needed to support electric transportation and a renewably powered global transportation system. as I mentioned, lithium ion chemistry will dominate in the next decade. New battery chemistries may certainly find a niche like the solid states. And the problem of cobalt and nickel, cobalt is very rare. The Democratic Republic of Congo makes 70% of the world's cobalt. They've got child labor issues, and so there's definitely a supply chain issue there. That nickel and cobalt chemistries are coming up that's going to be replaced, both of those, with iron and copper. At least that's the prediction that we see. The other huge issue that needs to happen in lithium ion, and you see this on Tesla's battery day, they've already started to increase the amount of silicon content of the anode to replace graphite. Silicon, however, expands 300% between 0% of charge and full charge, where graphite expands like 5%. And this expansion can cause mechanical degradation in the life of batteries. So this is a challenge that a lot of people are working toward. Tesla has one kind of a solution. So in any event, battery manufacturing is the current limit for EV production. There was a time when if you tried to buy a Tesla, they were limited by how many batteries they could make. You couldn't even get a Powerwall delivery because all the batteries were going to vehicles. And they still are battery limited. You also will see a lot of other car companies, Volkswagen and some of the other bigger players, there also will be battery limited. There's a lot of new cars coming, and there's some great, awesome cars coming out with, that could very well compete with Tesla, or, you see the Lucid Motors vehicle is an awesome vehicle. The Rivian pickup truck, the Porsche Taycan is a tremendous vehicle. Audi has some pretty compelling vehicles. There's a whole pile of awesome vehicles coming out. And some of them are even a little bit cheaper. In fact, I want to mention something I ran across here. You can order an electric vehicle on Alibaba, all right? And it comes from, let me see if I get my notes here. It comes from it comes in a box from a company called Changli. You can buy that electric vehicle for $930 and get it delivered to your door in a box, all right? Of course, it would be $1,200 if you wanted to include the battery, but it already comes with a backup camera at no extra charge. So imagine you could buy a car for $930, all right? I'm pretty sure this is not a super high quality car, and it doesn't have very much range, obviously a city car, but for going grocery shopping, going to the doctor in the city where you only have to go 5 or 10 miles at a time, wow, it's an interesting possibility. Not so conducive to our suburban lifestyle, however, in the US. You saw a few curves. I'm going to throw a few curves at you right now. This curve is called the duck curve. It's a famous curve prepared by CAISO, the California ISO, or California grid operator. And it was kind of noticing the projection of how much power they needed to provide on the grid with all this increase of solar. And as solar gets more and more popular out in California, a very sunny place, then the problem is that all the generators during the day don't need to run because solar is the lowest cost producer of power, and all the natural gas and ramping capabilities ramp down. And then as soon as the sun goes down in the evening, they have this problem with an increased ramp rate. In other words, somebody has to come and make power someplace. On one hand, batteries can certainly help and deal with this increased ramp rate. You saw that Moss Landing has, for example, a big natural gas planned system for peaking units, has largely had lost some of its future natural gas production to batteries systems, and battery systems can certainly provide a great amount of power in a short amount of time and help to stabilize the grid as fossil powered systems. So this is another curve which we're going to call the dragon curve. When you start putting the chargers like you guys did at VTA, 1.5 megawatts here, and where you have car chargers alone that are consuming, that can provide 250 kilowatts of power to a charger, all of a sudden you could get an awful lot of big bumps on the grid. This is actually a relatively small problem for the utilities. It could be a problem that if you want to locate a level 2 charger at a specific location, that the grid may have to increase the size of the cables going to that location, or make some adjustments so that the voltage will be regulated properly. But actually, the utilities are looking forward to the electrification of transportation. It's new business for them. They're also looking forward to some of the problems. And I know Edward showed this curve called the shark curve, and utilities are definitely concerned about this. We see the utilities in Massachusetts very concerned that everybody comes home, plugs their electric car in at 6 o'clock, especially on the hot summer days where we're at peak load, or down in Texas right now where, you know, they're at peak load in the evening with heating. And this could add a considerable amount of stress to the grid, but this is actually a very manageable concern. And I'll show you some examples of even what our own little utility has done to do that. Basically, they are going to encourage you to charge at a different time of day. All right. You know, in many locations, the metering for your electric power is constant. It's the same price day or night. You know, some people have time of day metering. Eventually, we may see the grid interactive home where smart meters are adjusting your power continuously throughout the day like other larger players are. So, you know, you heard this term V2 something, wasn't it? What was this V2 stuff? There's V2B for vehicle to building, vehicle to grid, vehicle to house, you know, and the vehicle to grid is a common thing. That basically is a two-way bidirectional charging system. You know, an electric vehicle like say a Model 3 Tesla, which I'm familiar with, has 75 kilowatt hours of usable power. You know, that's equivalent to like 4 or more power walls that could power my house actually for 4 days straight without any sun. I just can't get the power out of the car. So far, Nissan was supporting that for a while. Actually, you know, the first Teslas, the first Roadsters actually had vehicle to grid, but nobody seemed to use it. And I'll tell you why nobody used it. Nissan enables that in their EVs in Japan today. And I think you're going to see vehicle to grid become much more popular coming into the future. I'm not sure all the places it happens in China. Very much more popular for school buses, as we've seen, because there's a good match to when the vehicles are needed compared to, you know, because the primary purpose of a vehicle is to transport something or somebody. And the secondary purpose is to become a grid scale battery. But nevertheless, they can still serve those two functions from time to time. I actually show you my own V1G system, all right? So vehicle to grid looks basically like this. If you have a battery and an appropriate bidirectional charging system, which is, by the way, it's not that hard to take a 350, 380 volt DC power source and put an inverter on it and make AC. In fact, you could put quite a bit of power back into the system. You know, the amount of power that comes out of the battery to propel this car, you know, is pretty big. It gets up to 300 kilowatts. All right. You know, you could put one heck of a lot of power out of a car. Maybe you wouldn't have that big of a bidirectional inverter, because that's actually pretty big, more than the use of the car, maybe more proportional to a 30 amp breaker on a 240 volt system. That's kind of the level 2 charger typical size. But anyway, vehicle to grid I could imagine that if you had 270 million electric vehicles, eventually, the number of vehicles in the US that were all electric and they all had vehicle to grid, that it could really have provided the Texas a great deal of assistance to power through some of these grid problems that they have here in the last week. Obviously, that's long term. Then to get to 100% renewable, 100% EVs is, I don't know when or ever if that happens. But electric vehicles are definitely going to be climbing, and they're going to be a big impact. In fact, of all the lithium batteries made, about 90 to 95% of those lithiums go into vehicles. So all this talk about these big grid scale batteries, they're actually a pretty small entity in terms of energy storage compared to the energy that's available in those electric vehicles. Basically, that electric vehicle you should be looking at it as a portable generator. In principle, you could put a backup panel. I actually saw a guy that had a Toyota hybrid vehicle, and he actually put an AC power plant in the back, so you could plug 240 and 110 volts in the back of the car, and he would use it to power event tents, you know, in rural areas. And basically, when the battery in his car got depleted, the engine started and charged up the battery, and he could basically power an event for quite a long time out of the back of his car. So this is actually a photograph of my own ChargePoint level 2 charger, rather. It's what you would call vehicle V1G. And in fact, our utility has a program because we want to avoid those peak loads. And it's administered by MWIC, Mass Municipal Electric Company, in several different municipal utilities And basically the utility agrees to give me a $600 ChargePoint charger with the stipulation that it must be connected to the Wi-Fi and stay connected, and that the utility can reduce the charge rate during peak load events. So on very cold days or very hot days, I would get a text message just like the one shown here. The service provider has reduced the power on your CP home, the name of my network, due to high energy demand. You may be charging at a lower rate. And it basically bumps it down from level 2, from 30 amps down to, I don't know, I don't even know what it is, 5 amps, and then say someplace around 9 or 10 o'clock when that event goes over, it would allow the charger to go back to a normal level 2 rate. It really is pretty harmless in the vast majority of cases. I don't really need to charge between 5 and 10 p.m., which is the most likely place where I would be curtailed. So smart grid and, is missing something, all right? The smart grid and smart home is missing something big, all right? And what it's missing is the financial incentive for people to participate and contribute, all right, to the electric grid. Right now, the average consumer just plugs in power when he needs it, doesn't have to worry, whether it's the utility is struggling to provide that power or not, all right? And when all of the, in Texas last week, when the price of power went right through the roof for all of those people that are competing in the grid markets, all right? The frequency control market, the peak load market, the 1 hour look ahead. There's all these different electric markets that are managed by the electric grid. All the people in the homes had no such incentive. They just turned on electric heater after electric heater to keep their pipes from freezing, all right? And actually there was one utility in Texas that actually sells power to their customers at the, what's called the local marginal price, the real-time rate. And they actually advise their customers to change electric providers because their electric bill is going to go through the roof. But that's precisely what was intended to encourage them to conserve. But clearly people are not yet organized to conserve power because they haven't got, and it's going to need a lot of automation for that to happen. But I always use this statement. A draftsman I knew in Texas once said this, and it cracked me up. Voltage moves electricity, pressure moves fluids, and money moves people. And so that's what's missing here. There is no financial incentive for me as a homeowner who cannot participate in the electric grid to push power from my batteries into the grid. And it's actually equally important, there's no incentive for me as a homeowner, even if I didn't have a battery system, to delay my electric hot water heater or delay my HVAC system because it doesn't have any financial impact on me. So FERC Order 741 took about 2 years to implement, and it allowed grid batteries to compete on the electric grid as a generating as a generating entity. FERC Order 2222 was issued in September of 2020. It very well could enable grid interactive homes because it basically requires that aggregators must allow small electric consumers, they must allow, the investor-owned utilities must allow aggregators to provide the same market services that are provided to other consumers and to distribute those amongst a large number of small electric consumers. And therefore, they can participate in all these ancillary service markets. If suddenly you have an aggregator that says, hey, I could have paid you a lot of money, you could save, I don't know, $100, $200, $500 a year if you could have participated in this, maybe more. It could be 25% of your electric bill you might be able to save with an aggregator by just shifting loads that are, in many cases, not hard for you to do. And in such a case, EV buyers will suddenly start demanding vehicle to grid. All right, I've already contacted Tesla. They won't. I'm just the rarity. I'm just the one person that could see the vision of vehicle to grid, and yet. I think you'll see a lot more demand for that. So as I mentioned, my own EV could power for 4 days. The first Tesla Roadster had it. If EVs dominate the 65 million cars sold per year, this could play a huge role in flattening out the grid, tremendously reduce the amount of investment that electric utilities have to make in transmission and distribution, and also new generation assets. There's a lot of generation assets here that sit there and are operating for only 1 to 5% of the year do they actually ever operate. They just sit there and they're paid to be ready to generate. And obviously there were a few in Texas that weren't quite ready. All right. And in fact, there was a few people that were just trying to generate that had problems. A couple of big gas peakers died. So imagine that you had real-time pricing at the residential level and that you would suddenly be able to deal with this. There are companies like Ohm Connect is a California company, not too far from you guys in California there, that operates an aggregating system that allows consumers to participate in incentives to smooth loads. And they make it more like a video game, and they helped with the automation. One of the problems, of course, we have is long-term storage of weeks or seasonal will be much more expensive. Vehicle to grid doesn't solve that problem. Lithium batteries don't solve that problem. In order to store energy long-term, you need to move it into chemicals or some big gravity entities like a large body of water that, like a pumped hydro system or some hydro systems took 3 years to fill. But so there are some options there, but it's a hard problem to solve. Just a couple more things I'd like to mention. Of course, there's kind of a mess in terms of charging cables out there. Tesla just launched ahead and put their own charging system in, and it really is quite superior, I think, to most others. They're all level 3 chargers. You can charge easily at 600 miles of range per hour. Many of these other level 2 are also out there, CCS. Unfortunately, if you have a Nissan or a Volkswagen, you can't plug into the Tesla proprietary system. Tesla, on the other hand, has adapters that allow you to plug into the CHAdeMO and or CCS. CCS looks like it's kind of the emerging standard. It would have been sure nice if we actually had a government that said, no, we're going to go with one standard. It's going to be CCS, whatever, type 2. All right. Every car company must provide a CCS type 2 charger, and every CCS type 2 charger must be able to provide whatever 200, maybe a different level of kilowatts of power. Also, just because of the charging cable and charging infrastructure, there's a lot of issues with electric cars. In a lot of cars, battery systems cannot take charge at that rate. And it's interesting to note that, the charge rates vary depending on vehicle type. And here I show a couple of different vehicles, and some of them are slow to charge. Some of them are faster to charge. And the charge rate varies by the charger capability, and also by the state of charge. Batteries will charge much faster when they are nearly empty. And as they approach nearly full, to protect the battery life, they charge at a much slower rate, right? Much, much slower, less than half the rate, for example. Also depends on battery temperature. Cold batteries need to be limited how fast they can charge. And in fact, many batteries actually preheat the battery before the charger occurs. And I'm just giving a credit to Inside EV's website for this graph. In any event, those are a few things I thought that would get the discussion going. I can see we have a few Q&As, and I'm going to stop sharing right now, and maybe we can get into the Q&A.
Thank you, Rick, and thank you, Gary. I think we can all agree that those were phenomenal presentations. We really appreciate it. Okay, great. And so that concludes the presentation segment. And now we'll move on to the audience Q&A. We have quite a few already, but as the last few come in, I just wanted to throw out a few points that I had, or a few questions that came to mind for me. So Gary, could you possibly talk about a little more about the economics of your EBOS deployment? How much you saved on operating cost and maintenance and the payback period?
Well, so I guess I would have to say is that it's still a little bit on the skewed side, because when we bought the Proterra buses, we bought them under warranty. And so they're basically under an extended warranty. So we actually don't repair the buses at all. It's all figured into the original purchase price of the vehicles. So the maintenance side, where we don't really have as much data, or you could put it the other way around, because it's under warranty, it's great.
Zero.
It's zero. And we know that we're saving at least, from comparing the fuel cost of our hybrid vehicles versus our electric vehicles, that data showed that we're definitely running, at least half the cost on fuel right now on the equivalent of fuel cost. So, so between those two together, it's actually is a pretty bright picture. Of course, as they finally start rolling off of warranty, then we'll start doing some of the maintenance issues. But so far, we think that shouldn't be a problem. The drivetrain has been excellent, and the bus and the batteries have also, the drivetrain batteries, all the electronics has been really bulletproof.
Mhm. Okay. Yeah, and even considering that you're still in warranty, do you have a rough payback period that you're kind of going with internally?
That's a really good question. I don't think we've calculated that one.
Sure. Well, I know part of what's driving the decision was regulation. It's not just financial for you guys, of course.
Yeah.
Yeah.
And one of the challenges is that Gary, has these buses for 10, 15 years, maybe more, and the rates can change every couple of years. And so you can do a case saying, oh yeah, this is going to have this kind of payback, and it'll actually change based on the dynamics of the rate. You also have a system that's flexible, so you can adopt to the rate, so you can move when the rates move in your energy management.
Mm-hmm. Yeah, we had a question from the audience, and I had the same question written down. Gary, you mentioned that that peak rates in California, the schedule is changing soon, and that peak rates are moving from midday to after 4 p.m.
Yes.
Now that's conspicuously in line with the shark curve and the duck curve and all of that.
Right.
Do we think that that's related to the high penetration of EVs and solar in California?
Yeah, it's definitely, it's due to the solar side, because as you know, California by far has more solar on the grid than anybody else. Well, we'll just take our Cerrone yard. So we've calculated that at our Cerrone bus yard, just the reduction, so today we're selling a considerable amount of energy back onto the grid during the middle of the day. And the amount of money we're going to get for that solar energy is going to reduce by $50,000 a year. So we'll get $50,000 a year less in that, which now makes energy storage that much better, viable, and to store that energy and use it later, and then get that $50,000 back is an example.
Yeah, and just to give a benchmark, roughly how much of California's generation is solar? Is it 25, 30?
Well, I think they actually hit one day, it was at 50%, but that was I think for a 1 day peak, it actually exceeded 50%.
Mm-hmm.
But I don't know what it is right now. Oh, Rick might have a better feel for that. I don't know.
It's high though, even on
But
average.
it is very high. Yeah, California
very
is, one of the highest of all the states.
Yeah, California and Hawaii are the states that have so much good solar that they start getting into this problem of grid management, and to some extent they discourage new solar generation unless you put it in with a battery and start shifting your load. And so in many cases, the only way to add new solar installations is to include a battery storage, or else it doesn't help. It destabilizes the grid too aggressively.
Mm-hmm. Yeah, that's partially the effect that the new tariff schedule is having as well. And we actually had a question about that from the audience. So what is the backup plan for charging vehicles if there's a long-term power outage and the sun isn't shining? This has happened with major weather events like tornadoes, hurricanes, ice storms.
Well, we currently have a dirty diesel generator on site. But we're actually talking to a couple of other companies about maybe using thermal energy, where where they would have a thermal plant, which could be from biomass or from solar, from thermal solar, and then that would then be stored into containers, and that can store that energy for weeks. And then that can be transported by, truck into the facility and then run off of a hot air, diesel generator.
Okay.
I mean, I would agree. It is a difficult, the question asked is one of the most difficult things we have to deal with. How do you deal with long-term energy outages and storage? That will certainly deplete any lithium batteries you're likely to be able to afford. And so lithium is great for 4 hours, maybe even overnight. But if you have to get an ice storm, obviously you can size your battery. As I mentioned, vehicle to grid would be a great way to have a battery. We had an ice storm here in the town of Princeton, here where I live, that knocked out power for 12 days. All right. But some of the local communities had power. So basically I could just power my house for 3 days, drive my Tesla over to the charger, charge it back up and power it for another 3 days. It's a lot better than going to the gas station for gasoline. But clearly diesel and gas are very good. There is some possibility that someplace in the future, hydrogen could be used. Once you make hydrogen, you have the option of converting that hydrogen to methane or even to liquid fuels. There is chemistries available to make hydrogen into diesel and gasoline.
Can we maybe speak a little bit more on the energy management platform? Maybe this is for you, Paul. Gary mentioned up to roughly a 20% energy savings already.
Yeah.
Can you speak more about that?
Yeah,
and how that works on the back end?
So in California, there actually are 3,000 utilities. In California, in the United States, there are 3,000 utilities, each with their own tariff, and so it depends. And so some tariffs are demand charge only. It doesn't matter how much the cost of the kilowatt hour is the same, but the demand charge is where all the excess cost is. Sometimes it's time of use, right? Sometimes it's a combination. And so we run an optimization engine that knows how much energy to provide by what time, knows the tariff rates where the time of use steps up, and knows the cost of excess demand, and knows the demand so far this month, and takes that and creates a solution set saying, here's the charge plan that will charge Gary's batteries safely, but as cheaply as possible on this day. And that's why we have all the interfaces to Clara devices and Trapeze, so that we know the latest. We know how much data charge when it arrives. We know the schedule of the buses and how far they have to go to create that optimized plan. And that's really the value of what Gary's put together with all these partners. And I would say that, with 10 buses, it's a manageable problem. With 400 buses, you better have a system that's well tested.
Mm-hmm.
So just as a follow-up to that, Paul, and maybe to Gary, we had a local utility put a 4 megawatt hour battery in place, and they realized that because they're just a municipal electric company, they're not manned 24/7. They go home in the evening. They come in if there's an outage. But they actually didn't quite realize it at first, but they needed to hire somebody to operate their battery. All right. Mm-hmm. And so they hired a local utility service company that actually monitors their battery in real time remotely and decides also based on the current price of electricity to help avoid capacity and transmission charges. They decide when to charge because they're looking at the market conditions as well. Do you guys, Gary, do you foresee that as one of the things, or maybe it's just a warning that you should foresee that in the future?
I'll let Paul first, and
Let me start first. So 2 things. One is that you need automation to get that price signal into your optimization engine. So you don't want a person doing that. You want to have rules that say if it goes above 12 cents, do this or whatever. And so that's important. But I think Gary does need to have 24-hour staff in case there's an error at the charger, error at the bus, and the charging process stops. Sometimes you have to go unplug and plug in. And so we send alerts off saying, hey, bus number 7 needs a little tickle to get it charging again. So that's where the change is. It used to be diesel fueling is a 15-minute process. Now electric fueling is a 10, 12-hour process. So.
Well, and then the advantage is that we do run a 7x24 operation. I mean, when buses are coming back, the majority of our maintenance is done at night. So when the bus fleet comes back, if the kids scribble their name in the back of the seat or all those other interesting things that kids do, right? Or, people or things just break, that all gets done at night. And so the bus is ready for pull out the next day. So we have a pretty substantial staff at night. So things like that, that needed to be done, we do have the people to go do them.
And Rick, I was part of a project, gosh, 5-6 years ago now, at the Los Angeles Air Force Base. And our software was actually bidding 29 vehicles into the regulation market. So we got a price signal every 4 seconds and decided whether it's plus 200 kilowatts, minus 1,000 kilowatts. And we moved every 4 seconds, we moved that load automatically. So that is certainly possible, even at those scales.
Wow.
Wow, automation. That's what we need.
Mm-hmm.
Right.
That's right. And
And if
Oh,
you
go
look
ahead.
at our kind of our lessons learned, our next 34 chargers, we actually planned on trying to supply a good percentage of that energy ourselves with 1.5 megawatts of solar. That's 1.5 megawatts per hour of solar, and storing that into a 4 mega, that kind of thing. So our whole intent was basically to try to, actually pull as little amount of power off the grid as possible. Maybe use it to help stabilize things, but to run our own facility, our power plant to almost extent, right?
And the energy management platform, of course, integrates with the solar installation and that system
That's right.
as well.
Yeah.
Yeah. And also with Trapeze and Clever Devices system, so your fleet management and deployment.
Yeah, so it's the hub. It takes all the sources of information in and decides how to charge, what the charge plan is, and when to send the red flag up saying, Gary, get in here.
Mhm.
Sun's not shining.
Mhm. Yeah, it's incredibly impressive. And Gary, now, of course, the ChargePoint solution, the EMP solution, came with the buses, or you integrated that with the buses. Um, was that fleet management software from Trapeze and Clever Devices? Did you have that before? Did you have that for your diesel fleet as well, or
Well,
did everything get
Trapeze,
softwared up when you upgraded to electric?
yeah, no, Trapeze existed already, and ChargePoint existed already. You can't run a fleet of that many vehicles without that software.
Right.
But it had no parameters for electric vehicles. That's the key right there. So Trapeze, needed to comprehend battery sizes. It needed, those kind of things. ChargePoint or Clever didn't care about what the weather was, but now it does.
Mhm.
Those kind of things. So there's a lot of new parameters and new pieces of data that got integrated into the applications, and a lot of new, what I would call alarms. So we try to run the whole system off of alarms to a large extent. So that way the dispatcher, I don't need an army of dispatchers. The dispatcher is really waiting for an alarm to trigger and then go figure out, well, what's going on.
Mhm.
And we spent, I don't know, maybe a year around that big conference table in Gary's offices with 7 companies all saying, okay, I have this data. I know about this information. Let's talk about the use case on this workflow. So it was a non-trivial thing to put these various disparate systems together.
Yeah. Did you even find, Gary, that upgrading part of your fleet to electric helped you upgrade sort of the management systems for the rest of your fleet?
Well, I think it showed that electric vehicles without the management platform and all the other systems being upgraded was going to take a lot more manpower to manage a large electric fleet. And we could, and so adding another 4, 5, or 6 people just to manage, incrementally manage the electric fleet didn't make sense. Where automating all of these parameters and data elements and all that basically showed that we could use our existing manpower without adding staff to manage the whole electric fleet.
Yeah, and that'll become more important as you
As it gets
continue
bigger.
the expansion. Yeah. And
Yep.
could you just maybe share with us the e-fleet expansion plans?
Well, the next batch of, so we've got 34, so we got 10 vehicles now. We're working on another 34, which we hope to be able to add over the next couple of years. And so basically our intent is that by 2035, all 3 bus yards and all 400 and some odd buses will be, ZEBs. Now, we still don't know whether or not we're going to go, so we know that between 440 kilowatt hour buses and 660 kilowatt hour buses can take us to like 220 miles per day. But we actually run routes that are close to 400 miles. And whether or not those end up being hydrogen, fuel cell type buses, which is really more of a hybrid. So it's really electric bus with a, fuel cell, to help, supplement the electrical energy. Or we go with in-route charging is still up in the air.
That actually calls up one of the audience questions regarding hydrogen fuel cells and whether you think that will be, that has a role to play, especially for your longer routes.
Yep. So yeah, so we definitely, I think the verdict is still out on that. And I think we're thinking that over the next 10 years, hydrogen will also have some, both the hydrogen vehicles, you do pay more for a hydrogen vehicle than even an electric vehicle today. And then, it's pretty, costly to set up the hydrogen fueling stations to bring in, those kind of things. And if you're trying to use solar and making hydrogen and that process today is still pretty inefficient and very costly, but it's improving we're seeing improvements in that like every year.
Mm-hmm. Yeah, just like with lithium batteries and just
Yes.
like with semiconductors and telco and everything else before
Yeah.
it. We have these exponential
And I think from a
improvements.
fleet perspective, that's why you got to be careful. You don't maybe want to, if you converted your entire fleet today and spent the hundreds of millions of dollars it would take to convert that, by the way, because a transit electric bus is close to $1 million. So think of it, we have 480 of those things. That's $480 million just to convert the bus fleet.
Yeah.
And then, not counting that, the electric infrastructure to go along with that would also be another 100 million. So you can see, so, where, so if we convert it over time, we'll get the advantages of, industry changes and enhancements between now and 2035.
Mm-hmm. And you get to learn along the way with a smaller deployment and use those
Yeah.
learnings to have a more optimal deployment as it grows.
Right.
We have a question here from Ravi asking about how connectivity in cars and within smart infrastructure can accelerate vehicle to grid and vehicle grid integration. So that's probably for Paul and for Rick.
So I'll start. So some of the protocols support information flow. So all the DC connectors that Rick showed, shows information about the vehicle during the charging process across the power lines. And so if you plug in a DC charge, the system that receives that, the charging system knows which vehicle it is, and it knows the state of charge of the vehicle that's provided. So then you could certainly have the information about how much energy there is. On AC today, there's really no information flow. There's some protocols being described. 15118 is one of the protocols, but on AC you don't get information about state of charge. So that's one answer to the question. The other answer is you have to think about if you have AC and you're putting that on your grid, you have the issue of UL listings. You now have a vehicle that's generating AC electricity for your house or for your building. It has to be certified. Whereas if it's DC, then the charger has to be UL listed, and that's what's putting energy on the grid. So there are still some questions about the best way to do that. Rick?
Yeah, I mean, obviously the communication is one aspect of it. I really don't think it's a hard thing to do. You know, it's been done by several other car companies. I do know that when you plug your vehicle into a DC charging station, first of all, there's no DC power at that moment on the connectors. So it's unlikely that you could get a shock if you're standing in a puddle of water. All right. Impossible. But, and so that communication has to get established, and then the charging gets connected. I don't know all the details, but I know there's some significant details in there, but it's, you know, this is just software. It's not that hard a thing to do. You know, there is still some hardware issues. You do need an inverter, and you need to have an inverter that is UL qualified and and meets the appropriate regulations.
Mhm. And there's a piece here with the data flow between um, the power grid and the current energy prices, your home, whatever management software you might have in the future for your appliances and your vehicle,
Yeah, so there's a
battery,
bunch
and
of
all of that.
information hubs. There's the charger, there's the charger cloud, there's the vehicle has a telematics system.
Mhm.
And so all those have to coordinate and talk to decide
Yep.
what's it appropriate to do.
And to your point, some of that's wired, some of that's wireless.
Right, and certainly
Um,
you can't put vehicle to a house connected to the grid, because you can't energize a live wire. Or when the grid goes down, you need to switch for safety to island it. So that's
Right.
again more infrastructure to build.
mhm.
But technically it's done. We did it 6 years ago with 5 different vehicle types and 2 different charger types. So it's not a technical challenge. It's an economic challenge at this point.
Yeah, to Rick's point earlier, right? Money moves people.
Right.
Yeah, that's a great anecdote. Let's see. I think we have just about a minute or two left. I think the last question here would be for you, Gary. You mentioned that your drivers, over the first year where they were, messing with these buses, they improved their energy efficiency dramatically. Could you maybe speak to the driver perspective and what kind of feedback did you get from them? Do they prefer the e-buses?
Well, I think some of them do and some of them don't. How's that? And so what we've done is we've been able to pretty much, the drivers who want to drive the electric buses, get to, bid on that and get to apply for that. And then we work with them. So we have a great training department that works with the drivers and provides them detailed data on what their kilowatts per mile is on each of their different legs of their block, so they know exactly what they're how well they're doing. And it's pretty much and they know what their friends are doing also, that kind of a thing. So that helps everybody kind of actually they know that they're the ones that are you know make a difference. And it shows in their ability. I mean, we've actually got some drivers that can do 1.5 kilowatts per mile
Mhm.
pretty consistently. And they've figured out that it's starting isn't as big an issue, and stopping is all everything.
Mhm.
So letting the bus bring itself to a stop versus putting on those heavy brakes and using those brake shoes, that kind of thing is where you really get that, the regeneration, and that's what get the distance.
Mhm. Yeah, so they get to sort of gamify their energy performance.
Yes, yeah.
That's great. I'll just end with this little anecdote. I was speaking with a police chief of a relatively small department, and they electrified most of their cruiser fleet. And he was talking about the how the officers felt about it, and he said that they were all skeptical at first, and this was sort of a Midwestern conservative place. They were skeptical of the EVs, but after a few months with them, if you took one in for maintenance and you made a driver or an officer use a gasoline car, he said it's like you took their birthday away. So they all loved it. So it's just fascinating. Well, okay, that's 4 p.m. So I just want to wrap up and say thank you, Paul, Gary, and Rick, for the amazing session, and thank you to our attendees for coming. We'll see you next time.
Thanks, bye.
Yeah, thank you,
Thanks,
everybody. Great.
And just a reminder, we do have that session in 30 minutes on connected vehicles. So tune in for that. Thanks, guys.
Bye now.
Thanks. Take care.